So let us now point something about potential games before we go on to the notion of the congestion games, which is of course connected anyway, and that is related to mixed extensions. We introduced that in order to discuss being dominated, but that's an important topic. We will see this in relationship to existence of Nash equilibria, and in general, that's an important topic. So get used to it. And I remind you that the mixed extension means that the new strategy set is all the possible probability distributions over the existing strategy set for each player independently. And the utility function is simply the expected utility under this probability distribution. Now, the topic we are going to study now, that's simply one important thing, and that's that if a game is a potential game, and I remind you that when I say potential, I mean exact potential, that's equivalent to saying that its mixed extension is potential. And the proof is as follows. So first assume that the mixed extension is potential, and let the p hat be the potential. Then the restriction. Oh, I should have made it differently. I need to fix that. Let me see how I fix that. Okay. So I fixed that now. The restriction of this potential on the set of pure strategies is a potential on the original game. That's our claim, and let's see indeed why that is. So for any strategy set of the other players, for any pure set and pure strategy profiles of the other players, and for any pure strategies for player I, just prove the restriction of p hat on the pure strategy set indeed fulfills what it needs to be a potential. So the utility difference when moving from SI to TI on the pure strategy set, of course, is the same as what we see when we look at those pure strategies as mixed strategies. And I remind you that we identify a pure strategy with the mixed strategy, which does that pure strategy with probability 1. So formally, of course, you need to write the mixed strategy which we identify with TI, but we can use that too. Customary to do it in game theory. So the utility of those by the definition of potential, and here we are in the mixed extension, the difference of the utility difference of the unique change in player, which is I, is equal to the potential difference between those profiles, right? Because player I changes from SI to TI when the rest play S minus I. So the utility difference of that player is equal here to the potential difference. And again, since that only on the pure strategies, it's the same as the difference of the restriction on the pure strategies, and therefore we arrive that the utility difference of the unique change in player, unique deviator, which is I, is equal to the utility to the differences of this original potential of the mixed extension restricted to the pure game, the pure strategy. So we have proven that the restriction potential of the original potential, which is given here for the mixed extension on the pure strategies, is also potential, or in this case for the pure game. In the other direction, it's also from the definition, but it's a bit longer. So what we have in the other direction is assume, of course, the original game is potential, and its potential function is p, and now we need to prove that the mixed extension of the original game is potential game. So, consider the following candidate for the potential. It's quite straightforward. Who is the candidate? And by the way, the proof, as I have mentioned, but didn't say, I've only written that, is by Shapley and Mondar, as most of the theorems in this topic, from the seminal paper of '96 called Potential Games, which I quite recommend to read. That's in the recommended literature read by. So, what is the following? Basically, the expected value of the potential. That's going to be the potential of the mixed game. Intuitively, that should work, right? The definition of the utility of the mixed extension is the expected value of the utility, and the definition of the, let me just go to those slides and to help. That the mixed extension is defined as the game with those independent probability distributions on the strategies of first player, second player, and so on to the nth player. And the utility is the expected value of the pure utility with the probability. Or if a game is a finite game, we simply look at the multiplication of all the players. What is the probability of a given pure strategy? And we sum that times the utility of the strategy for all the pure strategies. The Lebesgue integral, which gives us the expected value, simply is equal to the sum of finite games. Going back to the lectures, to our lecture today, we see that this expected value of the potential is also, in the same way as we just saw with the utility, is equal to the sum of all the pure strategies of the potential of those strategies times the expectation of that pure strategy. Times the probability, of that pure strategy. And then let's see that this Q is indeed a potential. So we need to show that for any mixed strategies of player I, it will deviate from one to another, right? And for any sub-strategy profile of the other players in the set of delta of others, and I remind you that the delta of others is simply the product of delta S of all those players 1 of I. We can express those mixed profiles, the rest play P minus I, and play I plays Q, or the rest play P minus I, and play I plays P. We can express, though, as the convex combination of pure strategies. Now, please take note that we now express that together as a convex combination. So we look at this Cartesian product as a set, and we express the element which we have fixed in this Cartesian product, which represents what was the strategy before and after the deviation, as a convex combination. It's one big convex combination. And then we have the utility differences of player I of the unique deviator, who deviates from Pi to Qi, when the rest play always P minus I, is, well, by definition of these utilities, we just write pure utilities and the probabilities. It simply stems from the definition, and we just express all those Pi minus I, Qi, and Pi as one big convex combination. then we can replace the utility difference of the unique deviator in the pure case by the potential difference, by the definition of potential. And again, going back and using the definition of this Q, we can replace the expected value of those potential differences as the difference of this. So from linearity, it follows. Okay, finally, let us go to the new topic, which, as I said, is the second topic that you can say in this chapter. The chapter was called Potential Games and Congestion Games because they are related. Actually, they are isomorphic, as we'll see. But on the outset, they may seem completely different. First of all, potential games are defined as a general property of a game, while congestion games are defined as a class of games with a very concrete common thing, shall I say, practice related. It's also a general property, but it's a much more concrete definition, which is definitely much closer to my intuition. So it looks different, but we'll see it's the same mathematically. So the intuition of congestion games is modeling common usage of finite resources, which of course rises in congestion. Congestion results in congestion, and then the usage is basically conditioned by that congestion. So the more players use a resource, the typically harder it is for each of them, the less each player gets, so to speak. So the definition of a congestion game is as follows. A congestion game is defined as the following: a 4 tuple, actually more than 4 because these and these are each n and m tuples respectively. So it's defined as the following tuple. Well, the set of players from 1 to n. M is the set of common facilities, those resources they may want to use, from 1 to m. The set of strategies, Si, which is a subset, each Si is a non-empty subset of the set of strategies. Excuse me. Tongue slip. It's a non-empty subset of the set of all the subset of the facilities. So a typical element of 2 to the power of m is a subset of facilities. So let's say facility 1, 2, 3. And so Si can be any subset of Si can include subsets of M, but it never includes the empty set. Okay, I guess I've confused myself, so let me just go from definition. It's very simple. It's just, as usual, a bit confusing with notation. M are the facilities. 2 to the power of m is the set of all the subsets of m. The set of all the subsets. So an element of this set 2 to the power of m is itself a subset. So for example, several facilities, that's one element. And a subset of, let's forget for example, for a second, that we do not allow for a set which includes the empty set. Any subset of 2 to the power of m is a set of subsets. So the set of strategies is a set of subset. A strategy is a subset. Okay, yes. Now it sounds clear. So basically, 2 to the power of m is the set of all the subsets of m. And a strategy set is maybe not all, but some subsets. Because a strategy, a single strategy is a subset. Let's say I take from the facilities, I take road 1, 2, and 5. These are the roads I take to get to my destination. That's a typical strategy. The set of all the possible strategies of a given player is a set of such subsets. A strategy is a subset, and the set of strategies is a set of such subset of facilities. Now, we don't allow one special subset there, and that's the empty set. So the empty set can never be a strategy. So a strategy of a player has to be some non-empty subset. Good. Let's continue. It's really not hard. It's simply that the strategies is non-empty subset of facilities. The cost functions allows defining utilities. Now the cost function it has an index j, and it goes from 1 to n. So for each, it has an index j, and the j can be any facility. For any facility has a cost, which depends on how many strategies include that facility. I remind that the strategy is a set of facilities. Now, basically, the cost of a facility depends on how many use it, how many players use it. And the cost function gives us the cost. Typically, the more the cost. So the cost functions typically are non-decreasing or even increasing. So the costs in the game are defined as follows: the final costs. And here we are talking about costs instead of utilities. And the equilibria are usually when nobody can accumulate or decrease the cost. And that means that I should have written here cost instead of utility here. But I just write utility because the C is already taken. But here we are using cost. So the cost of the game is defined as follows: for any facility and any strategy. Remember, strategy is a set of facilities which is non-empty. We define the load Lij of that facility under this strategy, which simply is the number of players whose strategies are included facility. That's the load. Now the cost of the facility for each player will be the cost of the facility on this load, and therefore the utility on the game here it's the cost of a player is simply the cost of all the facilities the player uses. So we go over all the facilities the player uses, look at the cost of each facility under the load. From the load, that's what we define. So they define a game, right? There are players, there are strategies, which are non-empty sets of facilities, and there are utilities which are defined using those costs. Now, let's look at a simple example. So, congestion games can model traffic like on roads or computer networks and using common facilities and all that. So, in this example, let's look at modeling traffic, simple traffic. So, you have two players, A and B. Now, the facilities are, of course, the edges between 1, 2, 2 and 3, 4 and 1, and 4 and 3, or 3 and 4. And the cost functions are denoted as C12, C23, C34, and C41, respectively. So the cost functions are first. Now, the strategies of the players are as follows. So player 1 wants to connect vertex 1 with vertex 3. That's the intuition now. The formal definition is, of course, the follows. The strategies of player A are 1, 2, 2, 3, or what is the other way to connect 1 and 3? 1, 4 and 4, 3, or 1, 3, 4. Does not matter which order we call. I should call each edge in one by one name, but since they are undirected, it does not matter. Now, player B has the strategies. Player B wants to connect. That's the intuition again. Those nodes V2 and V4. And the strategies of player B are therefore, what are the two possible ways? So to use these facility, 1, 2, 1, 2, and then to use 1, 4 for 1, or to use that way, and that's use 2, 3, and 3, 4. So those are the strategies, and knowing the cost functions, we can just write this game in a normal form. We can just write what is the utility, because of course the utility of, for example, if one player goes this way and the other player goes this way, then they both use C1, 2, and therefore this edge will cost them C1, 2 of 2, what this function gives for 2, while the other edges, they each uses that singularly, so that those edges will just cost them those C on one player. So we can just express those utilities given this definition, and thereby write it in normal form. You can do it at home as an exercise. Now you can also write the potential of this game. It's a potential game in particular, and you can also write this potential. And the question is, you can do it if you want as an exercise, but the question, I do recommend to do it as an exercise, but the general question is, which congestion games in general also have a potential? Because we've just taken a very simple congestion game, and as we could have seen, it has a potential, but which other congestion games have potential? And the famous theorem by Rosenthal says us that for any congestion game, there is a potential. For any congestion game is a potential game, and a general congestion game has the following potential. So you go over all those facilities that someone uses. So the union of all those strategy sets are all those facilities which at least one player uses, and you go over all the J's, all the facilities someone uses. And for each facility, you don't just look at the cost of the facility under the load, which eventually results. No, in order to have this potential, you sum the cost of that facility for all loads from 1 to the eventual load. That's how you do it. So the social cost, so to speak, the total cost will be, of course, just the sum of all those used facilities of the load which eventually results of this LJS, which eventually results under the profile F. But the definition of potential function, which has to be proven it's a potential, but this definition defines this function differently. And I claim, Rosenthal claimed, that it's a potential function for this game. And let's prove that. So it can be shown in several ways. So for example, we are going to show this actually in two ways. One is that you can just show this from the above proven characterization of a potential game. So remember that we use that idea that it's enough to look only at a closed path of length 4, and that was that I remind you this corollary. A game has potential even only for any couple of players, and for any strategy profile for the rest, and for any strategies for two strategies for one of those players, for I, and the other player J. This path, in total, the utility, if you add and subtract here, the utilities as written here, it's 0. That's simply this function we defined over this path. You can just show that this indeed will be 0. That's straightforward. Another, also quite a simple proof, which we are going to do now. We can just directly prove that. So we are going to prove that this function indeed works as a potential, so that the utility difference between two players is equal to the potential function difference on those two, the utility difference of a unique deviator is equal of the potential function difference on the two corresponding strategy profiles before this deviation has taken place. And that's what we're going to do. So that's the proof. So when imagine player I, some player changes strategy unilaterally, so she's the only player to change. She starts facing some new facilities M prime and drops facilities M prime, M2 primes. Now, the changes to utility, what are the changes? So over the M2 primes, she used to get nothing, but now she starts using them. So she starts using their cost, under the load, which has just grown by 1, because she has added to the load. Now, over the facilities she has stopped using, M2 prime, she used to pay for them the cost of the load, and now she does not pay. So that's something which she now does not have to incur. That's a total change to the utility, again, to the cost. I just call it utility because the cost here is defined as the cost of a single. That's a total change to I's utility. And that's exactly the change in the potential function when I changes as described. Because let's look at the potential function. So there are some new facilities we just have got a new player using them. So it is just under the definition of this potential function. That means that we have added the cost of the previous load plus 1, because the new player uses them. That's this part. And there used to be some facilities M2 prime, player I has used, but now it stopped. Used to use, but now it stopped using them. So the contribution to the change of potential is exactly that the load on those facilities has just decreased, and that's exactly by 1. That's exactly this part. Okay, so I have proven therefore that this function indeed works as a potential, so that its differences are equal to the difference of the utility of the uniquely deviating player, whoever this player is. Let's call the famous Rosenthal potential, or if not say which, it's just a potential. So we've just called that the congestion. Any congestion game is a potential game with this potential. Now, as you may already have noticed above, I claim that congestion games are isomorphic to finite potential games. And not only are they a sub case, but they're also isomorphic. Now to prove that, we need just to say what we mean by being isomorphic to the case, and we use this simple definition. So before we prove, we need first of all to clarify what we actually mean by that. So we use the simple definition as follows. So given two games on the same player set N, which can differ therefore by the strategy sets and by the utilities. The first game G has strategy sets S1, S2, and so on till Sn, and the utilities U1 and 2 and so on till Un. And the second game, which we call G prime, has the same player set, but its strategies are S1 prime, S2 prime, and so on till Sn prime, and the utilities are U1 prime, U2 prime, and so on till Un prime. So you have two games. We define them to be isomorphic. Basically, for each player, the utilities which a player gets are kind of the same. If you map correctly what the player does. That's the intuition. Now let's go to the formality. So for each player, there exists bijections. So it means that there exist functions which are one-to-one and onto. Well, there exists bijection fi for each player, which basically map each strategy in the first game to the strategy of the second game, such that the utility of the player, if the strategy are mapped according to those functions f, those bijections, the utility remain the same. And the isomorphism is, of course, simply the vector of those five functions. Basically, isomorphism means that with respect to the structure we are interested in, those games are equivalent. Now, we're interested in what players can do and what they get from them. Therefore, that's enough definition. That's kind of the intuition, but here was the formal definition. And the theorem by Monder and Chaffee from '96 is that every finite potential game is isomorphic to a congestion game. Now, we have proven that every finite potential game, that every congestion game it's finite by definition, and it's a finite potential. But now we need to prove that every finite potential game is also a congestion. So basically, we prove this isomorphism using two directions. We don't just give yes. I'm just thinking it's true. We've shown how we can take a finite congestion game and find the potential, and now we're going to show how we can take any finite potential game and build a congestion game which is isomorphic. But we don't show that there is going to be a non-to function, which is of course true. But anyway, so we can say that we are proving this isomorphism is not exactly as we have defined it, but we are proving this simply by taking a finite potential game, and now we showing that it can be that is a congestion game. So the theorem actually is as follows: every finite potential game has a congestion game to which it's isomorphic. It should be said like that. That's the exact theorem. I think that's actually yes. It's not defined what it means to have isomorphic classes of games. You see? Define what it means to have two games which are isomorphic. And therefore, this theorem, as I said, makes sense. So every finite potential game has a congestion game to which it is isomorphic. But we're not defining what it means to say that the class is cyclic. But you see in which sense we mean that. Formally, what we say is that for every congestion game, we can show that it's a finite potential. For every finite potential, we can find the congestion, which is isomorphic. So the class equivalents are proven simply using two those statements, one of which we have proven and one of which we are going now to prove. I mean, this one was the one that, we're proving this statement using the definition of an isomorphic game. So we now prove that every finite potential game has a congestion game. We need to construct them, which is isomorphic. So we need some notation. It's not hard, simply requires to get some definition, to get some intuition about the notation. So the notation is as follows. Given pure strategies S1 till Sn, well, it's always pure here. Given strategies S1 till Sn, and a set of players K, capital K, denoted by S of K, so to speak, S is a parameter K, to be all the utilities which those players in K use in this strategy profile. So your union of Si when I goes over K. Now, so that's the basic idea. Then you have S minus K is all the utilities which are used by others. For K's which are singletons, you can just say instead of S of the set, including I, as we've just defined before, you can also say S of I. That's short, and then also S minus I. So what the others do, you can use that like directly instead of saying S minus the set, as we used to do before. So S of something is the other utilities which those use. And then for a given vector of facilities, of real numbers per facility, and for subset of facilities, we just look at, we say that X, again, is a function. X, when you apply it on B, on the subset of facilities, we just sum all those real numbers which refer to the facilities in B. So there you just united the used facilities. Here we just sum whatever we have in X over those facilities. And then we have a lemma which we actually maybe it's we could have not said that here, but it's a good, anyway, that's the lemma we use, and that's a very simple lemma which actually helps us to see that we have understood those definitions. So that given a congestion game, for every number in the set of players, so for any number from 1 to the number of players, define X, vector X with the index for R, so for this R, a vector of the length M, which basically tells us what is the conjunction, what is the cost of facility X, so J, if there are players who use it for every facility. So X of R, it's kind of confused maybe. XRJ is SJI. It's not confused, but it's confusing. What I mean is that X, the vector of a given player at place J, is basically how much this J's facility costs if exactly that number of players as this player's index, well, R is some number in this set, use that. So what's the cost of the facility? And then the statement is clear. It actually is, the lemma statement of the lemma is shorter than its proof. So it's something which is definitely just relying on the definitions. So it's like more an observation. Mondar and Shapley call it lemma. So for any player and for any strategy profile, the utility of that player under the strategy profile can be represented as follows, using our notation. That's basically the observation. The utility can be represented as follows, and we can just read this. You read this. So it's x1, the cost when one player uses that facility, for all the facilities which are only used by I and not used by the rest. So S of I, remember this notation, all those who are used by I, and the rest complement, and not used by the rest. So by one player who is actually I, so with some total cost. Then the cost of those who are used by two players who are I and some k which is not equal to I, and the rest don't use it, and so on and so forth, till those who are used by n players who are just all the players. And that's exactly the proof. The total cost of the facility is used by I only, plus the total cost of the facility is used by I and some other player, any other player, and so on. And that's the total cost of the facilities in general for player I. So again, that's just the understanding of this notation. If you read the proof in Mondar and Shapley up to the names, which I found maybe less useful for us, they are doing what I'm doing here, but they also give some details you may want to read. So please don't stop from reading that. Of course, that's not something you have to know. That's just if you have time and desire. Now, the proof of the theorem itself is as follows. I'm going to give just a scheme because it's quite long, but the scheme is quite simple. So, given a potential game, we define a game which is a congestion game, which is isomorphic to the original potential. So the potential game is N. The strategy set, I call them A, or they call them, I think. Anyway, and it's a finite potential game, and the potential function is P. Now, for each player, let us just enumerate all the strategies. So let's look at AI and call the strategies of player I. We just call them something A1, A2 until AKI. KI is the number of strategies of the player. Now, the set of numbers from 1 to Ki is simply capital Ki. Okay, the number of strategies of player I. Capital K is the notation of the Cartesian product of those Ki. So the set of those, how many strategies the first player has, excuse me, the set of the numbers for each strategy of the first player, Cartesian product of that set with the set of the number for each strategy of the second player, and so on. Now, let us define the following set of facilities we are going to use in our congestion game, and then the vectors of length Ki. I remind that the set simply that represents the strategies of player I. So 0, 1, Ki. So at each strategy can be either taken or not. And you just multiply it for each player. So this is the weird maybe, but that's the set of all the facilities. So we can depict it like here. So that set which consists of vectors such as some epsilon IL is some number not between in the set either 0 or 1. So from epsilon 1 when the superscript is 1, 2 till the number of strategies of player 1, they stand for they are taken from the number of strategies of player 1. Now epsilon 2 again 1, 2 till K2. K2 is the number of strategies of player 2, and so on. And each one of them can have a 0, 1. So all those possible settings of that matrix with not matrix, because the K1 can be different from K2, for example. Of the possible settings of that thing is the set of the facilities. Now, For each player I, define the set of the player in the facility game. Well, the number of strategies has to be the same, because remember that we want to have a bijection from the original strategy set to the new strategy set. So number of strategies have to be the same, ki, and the strategy L, the Lth strategy of player I, is the set of all the vectors. Epsilon is the vector of all hash vectors, such that in the I, jth, in the IL place, it's 1. The rest can be whatever. Again, that's the definition of strategy set. So, given a game where for each player this is the strategy set, I defined ki and all that simply based on how many strategies that each player has. Then, based on those dimensions, we define the set of facilities. And then for each player, we define the strategy set. Now, a strategy set has to be a set of subsets. So every strategy is a non-empty subset of facility. So the Elf strategy of player I is all the facilities such that the non-empty set, all the facilities such that epsilon IL is 1. Now, and again, because of the lack of time, and I don't want to get into too complicated, let's say notation complicated stuff here. I'm just going to sketch the rest, and that's enough. So the potential function, which we assume there is, allows us to define cost functions, and so thereby finalize the definition of this congestion game. And then we prove, remember that so we have this lemma, and then we eventually can prove that the utilities which correspond to the corresponding strategies are equal as desired. Okay, if you want, you can read it. You don't have to read it. That's what we discuss a very interesting point, by the way, in the paper. How many strategies do you need to express, how many facilities do you need to express a given potential game? Because the number of strategies has to be the same by definition of isomorphism, but the number of facilities is not set. And we have a certain number of facilities here, all those vectors, right? But the question is, what is the minimum number of facilities such that we can express, such that we have a congestion game which is isomorphic to the given potential game? And that's a non-trivial question. From what I remember, they say that it's not the minimum possible, probably not the minimum possible here, but they're not sure. So it may be even an open question. I'm not saying it's very important, despite that the minimum representation in general in any domain of something which is about mathematics and science is important. But here, we are not going, of course, to go on into that. Okay. To wrap up what we've done, so we've defined potentials, many kinds of potentials, proved many important properties like existence of Nash equilibrium, like the finite improvement property, like the paths, characterization using the paths. We said that it can be used as a refinement of Nash equilibria, and also prove that the game is potential if and only if mixed extension is potential. Then we define the class of congestion games, and then we managed to say that these are the same classes. Formally, that means that every congestion game is a potential game, and every finite potential game has we can construct a congestion game such that the games are isomorphic in the sense we've defined. That's the isomorphism between classes, but it's better just to say that we formally defined isomorphism between concrete games, and for every congestion potential game, we can construct a congestion game which is isomorphic, and every congestion game, on the other hand, is potential. Okay. Just have to remember that potential and congestion games are the same in a very abstract sense, and every congestion game has the potential, the Rosenthal potential, and potential has those properties. That's the main part.
and see you on the next talk.